you're a cryptographer, you'll focus on something like symmetric crypto or asymmetric crypto, or you'll do MPC, or you do zero knowledge. You have an area of expertise, and you publish in that area. And occasionally, your tools require you to learn a little bit more about another area of cryptography, or perhaps even another area of computer science, like, let's say, programming language theory. For example, there's a lot of interest right now in verifying the correctness of cryptographic protocols once implemented. So you have platforms like EasyCrypt, so you now have to talk to a different field. But you seldom, as a cryptographer, will probably talk to somebody, let's say, in law and policy, or game theory, and if you do, it's usually for a particular project, and then you move on. The challenge of cryptocurrency protocols is that they're incredibly interdependent, and they don't work at all if you're missing one of these components. So it merges distributed systems theory, it merges PL, it merges cryptography, it merges game theory, and so forth. And it puts them together in just the right way that if you get it right, you end up creating something like Bitcoin or Ethereum, which is tremendously successful, at least in the market, and it does at least something it's intended. If you put them together in the wrong configuration, unfortunately, the whole system tends to collapse or never takes off. So when we set up our research agenda, we imagined that we would need to build a large interdisciplinary and also a global group, because no university is so excellent that it happens to have people from every single field who are good and who would also want to work on the problems we care about. So our chief scientist is based out of the University of Edinburgh. It's up in Scotland. It's a very, very good computer science school, traditionally good in programming language theory. Then we broadened the research base. And now we collaborate with people from Oxford, people from Lancaster, people from Kent University. As you can guess, we have a little bit of a UK bias. But we also work with people in the United States. For example, we have some collaborations at the University of Illinois, Urbana-Champaign. We're potentially going to be setting up a center with the University of Maryland, alongside some other wonderful people. And of course, we have the collaboration here at Tokyo Institute of Tech, as well as a collaboration, a smaller one, at the University of Athens, which is mostly to work with some graduate students there that do some interesting research. So what are some of the topics, and how does that research work? Well, I'll give you 3 areas that are pretty interesting and have a lot of interesting problems associated with them. So one is law and policy. So if you look at the existing regulatory structure for financial services, it's usually built in a configuration where you have the agency. So let's say you're talking about securities, so these are like stocks. That would be in the United States, the Securities Exchange Commission, or here in Japan, the FSA. Then there's the people who are allowed to do stuff. These are banks, exchanges, other regulated actors, and they have specialized licenses and very intimate relationships with the regulators. And then there are the customers of those institutions, who their behavior is mostly regulated through the interaction with the financial agency. And there's a lot of unspoken rules. For example, if you're a bank, you need correspondent bank relationships to be able to move money from one country to another country. If you accept high-risk customers, you can lose your correspondent relationships. So in a way, that's a regulated function that makes banks very conservative in terms of who they do business with, without requiring the regulator to directly intervene. When you look at cryptocurrencies, those siloed hierarchical structures about how you handle regulation don't work, because you no longer have a small group of regulated trusted actors who provide financial services. You've now pushed all of those capabilities to the edges of the system. And instead of having them siloed by country, and the interconnection points between country are tightly regulated, now you have a global financial graph, where anybody can send value to anybody else. So what does that mean? It means your standard notion of compliance, so know your customer and anti-money laundering, no longer works. It also means that all the ways that you control the flow of capital no longer works. So there's an open question globally, trying to be answered here in Japan by the FSA, trying to be answered by the Securities Exchange Commission, trying to be answered by the European Union, by Switzerland, by many actors all throughout the world, of how do we build a new regulatory model given the capabilities of this technology? Embedded within that question, which seems to be strictly legal, is actually a potential to apply really sophisticated cryptographic techniques. For example, the compliance system that we currently have with banks is that they're data custodians. So if you go and sign up for an account, they learn a lot about you. That's called Know Your Customer. So they get your passport or a driver's license, they get your name, your address. They collect a lot of data. and then they hold on to that personally identifiable information. And guess what happens if the bank gets hacked? All of their customers' personally identifiable information could get leaked. Furthermore, this is jurisdictionally dependent. This is one of the reasons why it's so hard for me as an American to get a bank account abroad. Because if the bank accepts my business, they also have to keep records in accordance with American standards and the local standards. So it's a very costly endeavor. In fact, more money is spent on compliance than pretty much anything else in the bank. And if you add up the global amount spent, it's about $500 billion a year. It's an enormous sum of money. Every 3 years, you could basically buy Tokyo with it. So, if you're going to change your entire regulatory system to accommodate cryptocurrencies, at the same time, you can have a meaningful discussion of how can we take 30 years of cryptographic theory that allow us to quantify things like privacy and trust and information sharing with much greater granularity and put math-based guarantees into it. How do we take that and pull that into the new regulatory structure? So the notion of like minimum viable escalation. So you can imagine in the future that instead of a bank actually holding records, you take your information, you put it into a data custodian that's specialized and that's audited by some third party, maybe a government, and they sign that. Then you could query, the bank could query on a transaction by transaction basis the records via like maybe a zero knowledge proof and ask questions such as, are they over an age? Are they a US citizen? Have they paid taxes on this transaction and so forth? Until they get to a certain threshold and say, okay, we know enough to say this is a safe transaction or that this is a blacklisted transaction and deny that. And if the entity then gets hacked, there's no PII there. There's no profile there. Well, the very existence of such a thing is a hard problem, and it requires good theory behind it, and it requires a deep thought about how do we actually apply that theory so that it's scalable and practical. It could be used with billions of transactions. And by the way, such a solution would be global, because your policy could basically be embedded by a jurisdiction basis, and it's almost like a library. So you say you have to ask these questions to do business in this country, these questions to do business in this country. The country decides the questions, the protocol's the same. So this is what I do, is I talk to regulators, I talk to governments, I look at the marketplace, and I come to my cryptographers and I say, it would be so nice if I had a protocol like this. Is this academically interesting? Is this something you think you could do research with? And they say, yeah, okay, maybe. Or they say, no, I'm not interested. But eventually somebody picks it up. They think about it for a while and they write a paper. Maybe the paper goes somewhere, maybe it doesn't. Another thing is we're very interested in the proliferation of cryptocurrencies into the developing world. I was recently just in Ethiopia, in Addis Ababa. And I was also in Rwanda and Kigali, invited by the president there. And so while there, we had a lot of discussions about how do we get digital currencies into the developing world. And here's the problem. They have an intermittency issue in that they really don't have good internet in most of the places. And even if they do, it's not reliable. So you really can't have a digital money, which requires you to be connected to the internet to use, in an economy where people are seldom universally connected. Okay, so then there's a natural question. Is there a way to make these systems work offline? And how can you do that? Is that a protocol? Is that trusted hardware? What capabilities would you require? And what is the trust model? And to whom do you trust? That's a security question. And there's a lot of good research that one can do. So actually our lab at University of Edinburgh, in partnership with Huawei, works with us on just these types of problems, where we're actually thinking about how do we use trusted hardware to have offline transactions. And can we make this easy? Can we make this scalable? And so forth. A final topic is game theory. And this is actually probably the bread and butter of the entire space. So if you build these protocols, especially the consensus protocols, you'll see this nifty little requirement, honest majority. Okay, so while the protocol can be secure, assuming honest majority, you have to ask the question, what incentive do people have to be honest? And is this incentive realistic as the network grows? So in the beginning, perhaps it holds, but as the network grows, the actors diversify, it starts getting a little unclear. A great example would be proof of work. So let's imagine for a moment that there are two prominent cryptocurrencies that have the same proof of work algorithm. And they have about equal hash power, and there's a miner who controls a very large percentage of that. Let's say 51%. Okay. And they can either mine chain A or chain B. So here's what they do. Let's assume that there's a functioning derivatives market and you can short sell. Well, what the miner can do is go ahead and destroy the first cryptocurrency with a 51% attack after buying lots of derivatives to short sell it, and then immediately reapply his mining power towards the other chain. He hasn't lost any value because he's still making now profit from the other chain, but he's made a windfall from destroying the value of the other chain. Okay, now some things had to happen, which were new factors to destroy your security model and make a gold figure attack practical. And that's the challenge with our space, is that the game theory side, the incentive side, is always changing. It's always morphing as these markets become more interconnected, as they grow larger. So we also do game theory research. We look into mechanism design, and we ask questions of how do we create the proper incentives for people to honestly follow the protocol. And in some cases, you have a carrot. That's because you're basically printing tokens with cryptocurrencies, so you can pay them to follow it, as Bitcoin does. In other cases, you can invent sticks, or if you can identify people in a network, you can prevent them from using the network if they have some bad behavior. Or impose a penalty, like you have to solve a puzzle before you can reconnect or something like that. So these are three things that we think about amongst a big collection of things. What also makes us unique is once we find solutions and we really want to build them, we're a very principled engineering company. Most of the people in this space, they hire full stack developers, and they follow kind of a Silicon Valley-esque mindset of move fast and break things, which is kind of funny. I would never want to ride on a train that followed that philosophy. Don't worry, we can always ship an update to the braking software after the train crashes. Yeah, good luck with that. Instead, we borrow techniques from the aerospace industry, from the healthcare industry, and we follow high assurance software development, which means we actually write formal specifications that are machine understandable. And then we actually implement them, usually using a functional language like Haskell or Scala. And even if we're crazy enough, sometimes we'll even prove a bisimulation between the specification and the code. This is not commonly done in our industry or in all industries because it's very hard, it's very expensive, and it's actually required us to recruit some very big people. For example, the head of our programming language group is Philip Wadler, one of the creators of Haskell. And we've also established relationships with people like Lawrence Paulson, the creator of Isabel. And if you look at our website, we actually have a lot of papers that we write that we don't submit to journals because they're mostly mechanizations or formalisms. Like for example, we wrote the very first formal specification for a UTXO wallet for a cryptocurrency. Bitcoin's been around for 9 years, but no one bothered to write one. We didn't like the fact that we just wrote a spec. We're actually proving the specification using a language called COC. And it's actually a very big endeavor to do that. So that's the other side of our company, is the ability to translate research into specifications and then implement those specifications in a very rigorous way. And it's also very satisfying for the scientists who work with us because you go beyond the peer review and beyond the publication, which is usually when your job stops. You actually get to see the things that you do turn into real-life products. And you have an assurance that the things that they turn into actually follow the things that you wanted, as opposed to what the engineer wanted, which is sometimes a problem. So that's IOHK in a nutshell. We're a global company. We have about 160 people. We operate all around, and we do research. And we love working with partners like you guys, and we love working with people who are looking for interesting problems. And in terms of engagement, all of the research that we do is open source. We don't pursue patents. And we do everything from set up labs, like what we've done here at Tokyo Institute of Tech, to also doing one-offs, where, for example, we want to make Cardano quantum resistant. So we're having a lot of discussions about what signature scheme should we use and what does it even mean to be quantum resistant in the context of cryptocurrency. So we retained Peter Schwab and Alex Russell and others, and we're having a discussion about what specifically we need to do to, and what signature should we use. Should that be hash-based crypto or lattice-based crypto and so forth. And those are other examples, like the network stacks of cryptocurrencies. It turns out that this is very under-researched, and they're very fragile. So we ask questions of, when you go from 1,000 transactions a day to 1 million transactions a day to 1 billion transactions a day, what impact is that actually going to have on your network? And when does it break? And how does it break? And how do you rebuild this system so that it's more resilient and scalable and self-healing? And also data relays and centralized, which it currently is not in a cryptocurrency. That's an example of how we think. We think at scale. And there's some things that are open research, other things that are directed research, and everything is open to the world. So anyway, thank you so much for your time, and we have some great presentations today about some of the output of this laboratory.